In this week, we will talk about some basic elements in reinforcement learning. We need some preparation. In addition to the Anaconda Python programming environment, we will need
an environment for the reinforcement learning, and that is Gym, which is provided by OpenAI. If you Google OpenAI, the Gym, it will lead you to the GitHub page, and please follow the installation instructions here. After you have installed Gym, you may notice that there are parts of Gym. What we will need in the class is only the basic part. So basically, if you follow the installation instruction here, you will have what we need in the class. But if you want to do more experiments, such as the demo I have shown in the previous classes this semester about how to build artificial intelligent agents to play Atari games, you will need more environment, which are also parts of Gym, but will take more time and space to compile and install. So you might want to follow further instructions. After installing Gym, you can create a new notebook somewhere, and please test this. Import Gym. Let's make the font a little bit bigger. So if the installation is correct, this statement will be executed without any error. And let's make a learning environment for experiment, such as we can do one environment called gym.make. The make function is a factory method which will bring you object of reinforcement learning environment, and Gym has a list of different test bed. The one we will use is called CART PO and version 0. Okay. So this is a reminder that the environment is ready. Let's do a reset of the environment. And a nice thing of the Gym is that it's a nice visualization of many of the learning tasks. So instead of only fitting the equations and consider the reward, policy, and tuning the parameters, we can actually see what is going on in the learning process. The method is universal to all Gym environments. It's called render. So now bring up a window. We now have some environment like this. Basically, it is a small cart, and on the track you can move the cart left or right on the track, and on the cart there is a freely rotating pole. The task is to try, kind of intuitive, keep the pole as straight as possible without falling by moving the cart. Let's try. The way we interact with the environment is called the step. In the step, we provide an action. This action has a range that is different for different environment. In this simple task, we can only choose from two actions. One is to move the cart left, and the other is to move the cart right, which are represented by 0 or 1. To check what is the available range of the actions, you can check the property attribute of the environment. It's called space action space Let's have a look. So action space is an object attribute of an environment. Here is the action space.n, that means number of actions that is available to us. In this case, we have 2. Okay, let's try. Step. Well, I don't know which those actions are representing, but assumably 1 for left and 1 for right. I suppose 0 should be for left and 1 for right. Let's try. Okay, and we need to render the environment again to see the result. It moved a very little bit, so maybe we can try multiple times. Again, well, this time it's moved obviously. Again. So that's the way we play with the environment. Let us try to move the cart right. Have a look. Well, look, it is although we have given its instruction to move right, but in the next step the cart actually moved to the left. That is because our cart has inertia built in it. So if you want to move the object right with a left velocity, I think you need to operate multiple times. Note the counting number at this part. So let's have a look. Oh well, the cart starts moving right. So that is our problem setting. Let's investigate a little bit further. If you have watched the pre-study video of the introduction to reinforcement learning, notice that there are some pieces of information we expect from the environment for each step or each transition of information between the agent and the environment. The most important information is the observation of the environment, which we call the state. The second piece of information is the reward the agent received from the environment. Reward. The third one, in some cases, including this one, the task is episodic, which means there is an end of the process. If the environment have entered the terminate state, it will not be responsive to any action anymore, and it will be remaining in that state forever. Using the less fancy word, that means dead. So it's done. And in the gym package, it will also, some of the environment will also try to tell you something more. That is all included in the fourth returned value, which is of no use here. If we do this step, now we can inspect what we get from the environment. Print state and print reward and print done. Okay, in the case if you use Python 3, look, the state consists of 4 numbers in this case, and the reward is 1.0. Done is false. I do not know the meaning of these 4 numbers, but presumably they might be the position and the velocity of the cart and the pole. But in practical tasks, in some benign cases, we know the meaning of the observation, but in many cases we do not know the specific or semantic meaning of all the low-level sensory data.
So, to some sense, a significant part of the challenge of building efficient reinforcement learning algorithms to train artificial intelligence to react good in an environment is to make sense the observation the environment feed back to you.
Now, although for these four numbers, we pretty much can interpret them, but we try not to do that. We will try to build the learning agent that make these numbers regardless of their physical meaning. And the reward here is 1.0. For this task, I know what it means that it reward you of 1.0 every step you keep alive. Okay, if you keep the pole straight without falling, for each step it gives you a reward of 1.0. So totally, this task will encourage you to keep straight as long as possible. And down means the pole has fall. Well, in this angle, it is okay. We can try to push a little bit harder, see what we have. Let's go all the way right. Oh no. Yes, we can do this, right. Now the down is true, but I forgot to render it, so let us do it again. Reset, and use this stupid policy of moving all the way right. See what we have. 1 step, 2 step, 3, 4, 5, 6, 7, 8. Look, in each step we receive a 1.0 reward, and the card continuously moving right. So far so good. Let's move a little bit more. Look, now the pole has been tilting too much. That's been considered as falling, and this task ends. So the structure of a reinforcement learning or evaluate learned reinforcement agent normally look like this. We have a main loop, let it go forever, and in this main loop we will have some agent at work, and let the agent accept the state, and let the agent select an action for us. Also, policy. So we will call an agent policy and give the policy the current state and try to receive the action from the agent. After we have determined which action to take in the next step, we will give the action to the step function of the environment. Okay, maybe at the beginning, let's say prepare environment and agent. The environment will return us new state and the reward, and whether the episode has ended. Okay, all the other part are superficial. So this is the main loop, and of course, if it's done, it's done. That's the main loop of a reinforcement learning process. Let's try to do that. It is very easy to prepare the environment as we have just done, and it's a good idea to have the state to be collected at the time we reset the environment, because when we enter the main loop in the first step, we'll need the state to provide to the agent to evaluate the policy for the current or the first step action. So before we enter the main loop, we need to have one state prepared. Of course, this rendering is optional, and we can actually put the step here. So we render the environment every step. For the agent, well, that is our focus of study. I would recommend a systematic design of the agent, which I will have a framework here. Let's check. Copy my code here. It will be available to you. Oh. So basically, I have implemented an abstract class, which is the structure of all possible agents should have. It needs to initialize itself as an object. Note, you need to inherit this class from the object so that its children classes work properly. It will have one handle, or we can call it a method, a policy, and the policy accepts a state and will return an action. But in this case, we just implement the structure of the framework. So we do not actually implement this method. If anybody try to call this merge method, we will raise a problem to them. Look, I haven't implemented here. I'm just here to mean the structure. And also, we will later have another method called learn. Learn is to collect the piece of information needed by a reinforcement learning agent. That is the old state, what action I have done, and using from the old state based on the action, what's the new state I arrived, and allowing in this process how much immediate reward I've got, and also has the episode ended here. So that's the structure of our agent. And now let's implement a working agent, which can be very dumb. Let's call it non-ceremonial name called agent 0, which is the child of our agent structure, an interface using the language of software engineering. Self. To have the subclass parent class structure properly set up, we need to call its parent class initialization method. Note this part is different from Python 3 and Python 4. If you are using Python 3, please Google initialize subclass Python 3. Okay, for Python 2, what we do here is enough. We call the superclass of this class agent 0 and give an instance of the self and call its initialization method. Well, this is the general way we do the initialization for inherited classes. Now we need to implement a policy. Of course, the signature or the kind of accepted the kind of accepted argument of the method needs to be exactly the same as its parent class. Okay, now we implement this policy. Actually, for a very stupid policy, we can just return go left every time. And also we need to implement the learning method. Okay, so just copy it here and well, pass it. This dumb policy does not learn. I am stubborn. Save it and create agent 0 agent ag0 because agent 0. Well, we have a typo here. Remove it. Okay, fine. So now we give our ag0 to agent. All the elements are done, and we can try our policy. Okay, check again. Well, really dumb. There's not much interesting stuff happening here. A very important a very important indicator of how well the agent performs would be, let me call it episode reward. The accumulated reward in the entire episode, which is not the part of reinforcement learning, but it's a very useful indicator telling us how well agent performs. We clear it at the beginning of each episode and accumulate the step-by-step reward to this variable called episode reward. It means increase it by this, and after it's done, we can print it out. Reward. Notice Python 3, Python 2 distinction. Try. Wow, it has been up for 9 steps. 10, 9, something like that. Could we do better? Of course. Even if we try to do nothing, I think it should be better than this. My imagination goes so far as, let us have a next action, right? And when somebody calls our policy, I just do an opposite action from my previous one, so that I just should try to wiggling or shaking in the original place without moving anywhere. So next. That is our new policy. Try to this. Well, look, much better than the one direction moving one. So we have seen that how a reinforcement learning agents work. But the question is, now we have a very dumb agent, and the question is, how can we make it actually working, make the agent smart, and can adjust itself to adapt to the environment and get better performance. The secret is, of course, to learn how the environment works, what is the appropriate actions during different situations, along with the process. So here we will have a piece of code that is the core of learning. If we perform learning, we would call the agent judge learn method of learning by providing it the old state, the action. So actually we do not need to provide the action here, because the action was given to us by the agent. But for convenience and for generality, we comply with the tradition of providing the action information here. And after taking the action, what is the new state? And the immediate reward, and also whether the episode has ended. So in this function, the agent will accept this piece of information, we call it the experience of one step of transition, and adjust its internal parameters so that the policy would become more reasonable and more profitable in future during the whole process. And of course, after we have provided both the old and the new state, we need to store the new state into the old state. State becomes new state. So this piece of information will be used in the next step, go from here to here, to determine the action of the next step using the agent's policy. How to perform the learning? There are multiple branches and a very rich families of methodologies, which we'll take a glance in class. And in the meanwhile, why not take a weekend home project to derive or to invent some of your own method. Try to let your agent be able to improve its policy along the process of reinforcement learning.